A ball starts at a height of 19.6 meters with a horizontal velocity of 10 meters per second. Using this coordinate system, the ball's initial x position is 0 meters and the initial y position is 19.6 meters. The initial velocity is 10 meters per second and it's in the horizontal direction. That means the initial x velocity is 10 meters per second. The initial y velocity is 0 because this vector has no y component. It only points in the x direction. Since this is projectile motion, the acceleration due to gravity, g, is 9.8 meters per second squared downwards. Since we chose up to be the positive y direction, then ay, the vertical acceleration, would be negative g, negative 9.8 meters per second squared. So that's our setup. Now let's see what this motion looks like. The ball moves to the right and falls down at the same time. What's happening to the x position over time? What about the y position? And what do you think is happening to the velocity in the horizontal and vertical directions? Are they increasing, decreasing, or staying the same? Here's some grid lines and snapshots of the ball's position at half-second intervals. How much does the ball move to the right during each interval? And how much does it move down? If we draw lines from the ball to the y-axis, we can see how the y position is changing over time. The spacing between each line gets longer. As the ball moves, it falls a greater distance in the vertical direction during each second, or each half second. Now let's look at the motion in the x direction. The spacing between each snapshot is the same. The ball moves the same horizontal distance during each interval. So why are the vertical and horizontal motions different? 2D projectile motion is one example of an important concept in physics that we mentioned in a previous lesson. An object's x motion and y motion are independent of each other. The vertical motion does not affect the horizontal motion, and the horizontal motion doesn't affect the vertical motion. We know that objects in projectile motion experience a downwards acceleration due to gravity. Since gravity only acts in the vertical direction, gravity only affects the vertical motion. So if we look at the y position over time, the ball is accelerating downwards due to gravity. That acceleration causes the vertical velocity to increase. The ball speeds up in the vertical direction and falls a greater distance during each second. This should look familiar because it's the same as one-dimensional projectile motion, sometimes called free fall. This is a really important concept. The vertical motion of the ball shot out of the cannon is identical to a ball falling straight down. The initial velocity is horizontal, so the initial vertical velocity is 0. That's the same thing as being dropped from rest, if we're only looking at the y motion. The balls have the same height and velocity at each time point, and they hit the ground at the same time. The fact that the ball is also moving to the right has no effect on its vertical motion. So why is the horizontal motion different? Well, there's no gravity in the x direction, so there's no acceleration in the x direction. Gravity pulls the ball down, but it doesn't pull it to the right or left. If the x acceleration is 0, then the x velocity is constant. It doesn't change over time. So the ball moves the same distance in the x direction during each second. We could think of the ball's horizontal motion as being identical to a ball rolling on the ground at a constant velocity. Or if we turned gravity off, the ball would move in a straight line at a constant speed. The difference between this path and the ball's actual path is the amount the ball falls due to gravity. But the vertical acceleration has no effect on its motion in the x direction. As an analogy, Here's a bird's eye view of a curling stone sliding on ice with no friction, which we used in some previous videos. This is 2D motion on a horizontal plane, so the x and y directions are both horizontal on the ground. If we give this stone a push in the x direction, so we give it an initial x velocity, it'll move in a straight line at a constant speed if there's no friction. Now imagine we attached a model rocket engine to the curling stone. When we light the engine, it causes the curling stone to accelerate. If we point it in the negative y direction, the y velocity will increase and the stone will move further during each interval of time. Now, what if we light the engine and, at the same time, we give the stone a push in the x direction? Now the stone follows this curved path, which is a combination of a constant velocity in the x direction and acceleration in the y direction. In this example, the acceleration is caused by the rocket engine. In projectile motion, the acceleration is caused by gravity. This picture will change a little bit when we have different initial values, but this is how two-dimensional projectile motion works. The ball has separate x and y positions, separate x and y velocities, and we use separate x and y equations. But we can take the x and y velocities and combine them to get the actual velocity vector of the ball at any time. We can draw the components like this, or we can draw them so they form a right triangle with the vector. V is the instantaneous velocity vector of the ball. It shows the ball's actual velocity through the air and the direction of its motion at each instant. This might be the first time we're seeing a velocity vector on a curved path, where the direction is changing. Notice that the velocity vector does not trace the path of the object. The path is curved, but a vector is just a straight arrow. The velocity vector is always tangent to the path, and it shows the direction of the velocity at one instant.